It's the very last Friday afternoon session, and we're all getting tired. So, a very apt topic is at such a time of the day and week. Couldn't we just somehow stop working ourselves and dump all this complicated work we're having on proving our theorems on the computers instead? And as it happens, this is exactly what Susanna is going to talk about. How to automate the proof search. So please.
So that's exactly the first slide. Can a machine actually substitute us? So I wanted to start with the first reference that I've heard of this proof search problem, which was this letter from Gödel to von Neumann. And he starts saying, I would like to allow myself to write you about a mathematical problem of which your opinion would very much interest me. One can obviously easily construct a Turing machine, which for every formula f in first order predicate logic and every natural number n allows one to decide if there is a proof of f of length n. So he defines this function psi f of n. Let it be the number of steps the machine requires for this. And now let's look at the maximum over any formula f. The question is how fast this formula phi of n grows for an optimal machine. And then he says one can show that phi of n is greater or equal to k times n. The proof is not on the letter, but he says this we can do. If there really were a machine that could run in this constant times n, or even constant times n squared. So I guess this was his notion of a feasible or efficient machine. This would have consequences of greatest importance. Namely, it would obviously mean that in spite of the undecidability of the Entscheidungsproblem, the mental work of a mathematician concerning yes or no questions could be completely replaced by a machine. After all, one would simply have to choose the natural number n so large that when the machine does not deliver a result, it makes no sense to think more about the problem. Yes, so this is the question we're considering. Is it possible that a machine actually runs efficiently to find proofs? Okay, so what we'll be considering is we have a CNF formula. We want a machine that is going to say sat or unsat, and also not only say sat or unsat, but output some proof of that, which can be either a satisfying assignment or a refutation, a proof of unsatisfiability. And clearly the running time of the machine, it has to at least read the input and produce the output. So it's at least the size of the input plus the size of the output. And we'll focus on unsat here, which is the most interesting case because here we have very short certificates. And this is, so Tony talked about this already. So the question is, for example, like what if f has a refutational polynomial size? Can I find it in polynomial time? And even can I do anything better than the trivial truth table refutation? And since the problem is in NP, if we're going to show any kind of impossibility result, any kind of barrier, it will at least have the assumption p not equal to np, because if p equals np, p equals np, then I can solve this in polynomial time. Okay, so this is what I plan to do for the talk. So Tony already talked about proof systems, but I'll just go over some example of proof systems and algorithms that search for proofs in these proof systems. Then I'll actually talk like theoretically about the problem, like what are known non-trivial algorithms and what are the known barriers. After that, I'll try to give a more historical view. And then, well, if there's time, I'll talk about some ideas behind the proofs, but I'd like to talk about some other also related questions. Okay, so some example of proof systems. Well, we saw this already recently. Well, we have tree-like resolution, and there's an algorithm. It's called DPLL, which is essentially searching for tree-like resolutions by considering this this search problem. So querying variables and backtracking whenever a falsified clause is found. So this was implemented in the when was it? Early 60s. And then there's another class of algorithms, CDCL, which is actually searching for resolution proofs. And there you're actually learning clauses. So the DAG that you get is actually it's not a tree, it's actually a DAG. So the CDCL algorithms actually find resolution refutations. Okay, then another way of searching for refutation. So Tony also talked about, we can translate clauses to linear inequalities. And then we can just do some integer linear programming. We can do linear combination of inequalities, and we can do some kind of integer reasoning. So there are different kinds of integer reasonings, but for example, here if I know that 2x plus 2y is greater or equal to 1, I can derive that, well, if I'm over the integers, x plus y is greater or equal to 1. So there are also algorithms that are searching for proofs of this type. And the goal is to show that there's no integer feasible solution. So this would be algorithms searching for cutting planes type proofs. Then there are the algebraic and semi-algebraic proof systems. So now we translate the clause into polynomial, and we also include these Boolean constraints. And the set of these constraints is going to be unsatisfiable if and only if there's no common root. So here we have Hilbert's Nullstellensatz, and we have Gröbner basis computations, which corresponds to the polynomial calculus proof system. So it won't really matter what the definition here is. Just remember we're working with polynomial equations. That's what matters. Then we have the semi-algebraic proof systems. And here the idea is that, so the way I'm defining it here, I still have polynomial equations. And I'd like to say that these are unsatisfiable if the sum of these polynomial equations is strictly greater than 0. Because if there were a satisfying assignment, if I would plug that in to all the constraints, I would get exactly 0. So if I can show that this is strictly positive, I mean every constraint is either 0 or 1 when they evaluate it on 0, 1 input. So if I can show that this function corresponds to a strictly positive function, then I'm showing that this is unsatisfiable. And now we can think, okay, how can I actually syntactically prove that sum of coefficients is strictly positive? And there are different ways of doing this. So this is perhaps not the standard definition you would find, but it's equivalent. And I think it's a nice way of thinking of these proof systems. So you would like to say that the sum of the constraints equals some positive epsilon plus something that is non-negative. And what this non-negative function is will define these different proof systems. So for Shirali-Adams, this non-negative function will be just a sum of these generalized monomials, which are just like these constraints, which evaluate to either 0 or 1, depending on what you plug in, but they're always positive. So this non-negative function will just be a sum of such constraints. So if I can prove that the sum of my CIs equals for some px of these epsilon plus this non-negative function, then I'm showing that it's unsatisfiable. Does that make sense? Another possibility would be that this px is actually a sum of squares. So that's also a non-negative function. So if I could write sum of CI equals to some epsilon plus a sum of squares, I would also be showing that it's unsatisfiable. And that corresponds to the sum of squares proof system. So yeah, so these are possible algorithms that search for proofs in different proof systems. And again, it won't really matter exactly what this proof system is. It's just proof systems are. We can think just of, we have here we're dealing with clauses. Here I'm dealing with linear inequalities, polynomial equations. Here I actually have polynomial equations and inequalities over the reals. And there, as Tony mentioned, there's this hierarchy among the proof systems. I actually have the arrows in the opposite direction as Tony. But you have some, so higher up are the more powerful proof systems that have shorter proofs. Okay. Any questions here? So let's look at some of the algorithms and barriers that we have for the different proof systems. So just to, so Tony also gave the definition of automatability, but I'll repeat it. So we have some proof system S, and we say it's automatable if there exists this algorithm, that deterministic algorithm that will produce a refutation in this proof system, and it will run in time polynomial on the input plus the shortest possible output it could produce. So it, as we mentioned before, the best possible running time is it has to at least read the input and produce some proof, and this is the shortest possible proof. And we're asking for polynomial in this. So this would be automatability. And then we can also define automatable in time some f of n, if I allowed the algorithm to run. So for quasi-polynomial or some sub-exponential time. So the first results, so for tree-like resolution, so very simple proof system. Suppose there's a proof of polynomial size. Can I find it in polynomial time? Can I find it in anything better than 2 to the n? And this is a result from Bing Patasi from 96 that yes, we can do better than 2 to the n, not polynomial, but we can do quasi-polynomial. And this is a very simple algorithm, so I want to show you. Yeah, so this is quasi-polynomial in SNN. So to show this, I think it's easier to think of the decision tree. So this is equivalent. So let's think of the decision tree. And basically, we just have to figure out what variable we have to query first. And we know that one of the sides of the decision tree is going to be of size at least half of the size of the whole decision tree. So we will just recurse on that. So let's start supposing I know the size of the smallest proof. Okay, so suppose I know it's some s, and now I know that there will be one of the sides is going to be of size s over 2. So I'll just try all possible variables. There are n variables, and I'll try all possible assignments to those n variables. So I have 2 times n, and I'll call recursively the same algorithm with one less variable and with the size halved for one direction. And for the other, well, I also decrease the number of variables, but I can't say anything about size. So I just call it again with the same parameter s. So if I just solve this recursion, I get that the running time is going to be n to the log s. And the fact that I don't know s to start with is not a problem because I can just run this for s equals 1, 2, 3 until I actually get a refutation. So just add a factor s there. Okay, so this is a quasi-polynomial algorithm automating tree-like resolution. And then, well, we can ask, can can we do better than this? Can we do it in polynomial time? And actually, well, we have one barrier for this. If we could do better, then ETH would be false. So what we know is that if I could do n to the log 1 minus epsilon s, ETH is false. Even if I could do n to the little of log s, then the randomized version of ETH would be false. So there is some kind of barrier. I can't improve on that algorithm. So this is kind of like the ideal result we would like. We would like some automatability algorithm and then show that this is tight. Okay, so yeah, please interrupt me if you have any questions. So for resolution, the best automatability algorithm we have runs in time n to the square root n log s. So this is better than 2 to the n, which would be the trivial when, say, s is polynomial in n, when s is small. But it's not as good as for tree-like resolution. And the way this algorithm goes is, well, I can find refutations in time n to the w, where w is the smallest, the narrowest width I need for the refutation. So this, I can just look at all possible clauses of size w. There are n to the o of w of these. And I'll just try to see which of these clauses I can actually derive. And if I can derive the empty clause, then I know there is a proof of, I can find the proof in width w of size n to the w. So the way I get this automatability result is using Benson-Wigderson. There's a classical relation between size and width. So they showed if there is a size s refutation, then there is a width square root n log s refutation. So using this relation is how I can get that running time. So again, yes, yeah, good. So the formulas we start with, I have bounded with. So we can ask again, can we do better than this? Can we do like quasi-polynomial, like we do for tree-like resolution? And the first answer to this is, well, not via width, because this is pretty tight for resolution. So there are formulas that have polynomial size refutations, but that require large width. So I can't expect to using this kind of argument to get a better automating algorithm. But I can still ask, okay, is there another kind of algorithm? Can I do better? And this is this result from a few years ago from Mulat, actually showing tight non-automatability results. So if I could automate resolution in polynomial time, then NP equals P. In quasi-polynomial time, then NP is in QP, and even in sub-exponential time. So this is, yeah, pretty tight because it's in if and only if here. Okay, so again, yeah, we have we understand the automatability of resolution now pretty well. And then, okay, yes.
Do we know if n to the root n log s is tight under ETH? The width automating, like that could in principle be tight under ETH, right?
Yes, that could be tight. So Muller does not give that. It gives n to the 1/3 or 1/4. I'm not sure.
Yeah.
I think you can get this by modifying Muller a little bit. So you have to be a little bit smarter with like how you can't have these layer things. So I think it's doable and it's not hard, but it hasn't been written up.
Or just like width is n to the O W tight.
general, not if we're not talking about it.
Yes, yes, yeah, I didn't write that, but yeah, there are really formulas that can be done with W and that have size into W.
So what's the width tightness question? Sorry.
So here we have an algorithm that automates resolution in this time. And the question is this algorithm the best possible? And I think modifying that Diaz-Muller, you can get that this is pretty much, well, maybe you lose some log factors, but other than that, I think you get under ETH that this is. So yeah, so we can ask the same questions for cutting planes. And actually here, we don't know any automating algorithm. So anything that does anything better than 2 to the n, even if there's a polynomial size proof. But we have the same barriers as for resolution. So this was a generalization of Diaz-Muller. Yeah, but there's still interesting open questions here. Okay. And then we have the semi-algebraic proof systems. And here it's in some cases here we have as for resolution, degree D refutations can be found in time n to the d. And this is true for Nullstellensatz, for polynomial calculus over finite fields, for Shirley-Adams, and sum of squares under some conditions. It's also true. So, so this is part of what we need for an automating algorithm, but then we also need a relation between degree and size, because this would be degree automatability. If we're talking about size automatability, we want this relation between size and degree. And this we have for polynomial calculus, for Shirley-Adams, and for sum of squares. So that means that we get this same kind of automatability for polynomial calculus over finite fields, for the same one as we have for resolution and for Shirley-Adams, and under some conditions also for sum of squares. For Nullstellensatz, we still have the degree automatability, but we don't have the size automatability because this relation does not hold for Nullstellensatz. So there are some formulas that actually require large degree in Nullstellensatz, but have very small proofs. So, so yeah, it's also open whether there is some kind of automating algorithm for Nullstellensatz. So this is not known with regards to size. And then in terms of barriers, we also have this for polynomial calculus and Nullstellensatz, we have the same barriers as we have for resolution. Okay. And for sum of squares and Shirley-Adams, we don't have any.
That is restricted. Partial automatability for SOS, I think, and algebraic systems.
You know in advance the monomials?
The set of monomials used in the proof, you can search for the proof.
Ah, okay.
This was, I think, a acronym.
Ah. Okay, so you don't know coefficients? You know the monomials, and then you can search for the proof coefficient. Is that?
Yes.
Right? Okay, interesting. Yeah. I wonder how it works in sum of squares because then you would do degree automatability. Maybe there's some catch there.
Yeah, maybe.
Yeah.
For PC,
Yeah,
sure,
PC.
for SOS, maybe there's a caveat, but I don't think so.
Yeah, because there's some issues with coefficients here, but if they have small coefficients, then you could definitely see.
Yeah,
Okay.
just one consequence of what you said is a sort of like non-monodronicity of what we're in the sense that weaker systems will be automatable, stronger ones could be in between, you might not have strong consequences.
Yeah.
We don't have
Yes.
strong, we have strong squares. And it's similar to what happens with MCSP, where you might have hardness for smaller circuit classes, larger circuit classes, but not for ones in between.
Right, right. Yeah, that's a very good point. Yeah. Yeah, so here are some
Construct even the weird system with that property. Right?
Yeah, so it's only in terms of what we know.
Right.
But usually it's suitable.
Yes.
What about IPS? Is there anything?
Well, there is based on automatability results, because this is actually weak automatability, and then it's monotone, so it's for anything that simulates these proof systems. But in terms of automatability, I don't think so. Yeah, so for these Frege systems, there was a result of Krychek and Pudlak 98 showing that extended Frege is not automatable unless RSA can be broken by polynomial size circuits. And actually, yes.
I mean, as to what Rahul said, I mean, in some sense, we can define such proof systems that are not, I mean, in some sense, like, I guess, bounded degree, like bounded width resolution and bounded degree polynomial calculus would actually be examples of this proof search complexity jumping up and down, right? Nullstellensatz is like hard, then you sort of go to, in some sense, bounded degree, bounded width resolution, and it becomes sort of easier.
That's not
Well, you could somehow fix it and say, like, either I bounded width or else I have to fall back to tree like this.
okay. Okay.
So this sort of zigzagging that proof search is hard, and then for a slightly stronger system gets easier, then it gets hard again when you go to full resolution, and then yeah. So it's not just a, I guess, a theoretical possibility. It's like, but you're right that you have to define it a little bit carefully.
Yeah.
Yeah.
Right. So yeah. So here we actually Krychek and Pudlak, they don't mention automatability in this paper. What they mention is feasible interpolation, but automatability implies feasible interpolation, as Tony was saying, and even I'll talk about this later. Even weak automatability implies feasible interpolation. And this was later generalized in two papers for TC0 Frege and everything that simulates it, so that it's not automatable unless the Diffie-Hellman procedure can be broken by small circuits. So polynomial size for TC0 and sub-exponential size for TC0. So these are the results, and I just wanted to give like a taste of how this is proven, because it's actually like the idea is very simple. So first, we say that a proof system has this feasible interpolation property if there is a short refutation of this kind of split formula, then there is a small circuit that interpolates this, that given Z outputs whether A or B is unsat. Okay. So we'll actually use this definition of feasible interpolation. So the idea of the proof is I'm going to get some function, which is my assumption that this function is hard. So some function that is injective and is hard to invert. And I'll write this formula encoding that the last bit. So here I have some input. The last bit is 0. That equals Z. And if the last bit is 1, it also equals Z. And yeah, since F is injective, this is an unsatisfiable formula. So now suppose the proof system has, if we can show that the proof system has a short refutation of this, so if the proof system is strong enough, if we can, let's say TC0, we can show that it has a small proof of this, then if TC0 were to have feasible interpolation, then that would mean that I can actually say which of these two is unsat, which means that I can actually figure out what is the last bit. So I can invert the function. So this will show if I assume the function is hard to invert, then the proof system cannot have feasible interpolation. So that's the spirit of all of these proofs. Yeah.
Since you need a very specific assumption like ISA and
Yes, because I need to make sure that I can prove this upper bound. Yeah, in the proof system. So I find this like an interesting type of not automatability because it depends on proving some upper bound. That's why it only holds for these strong proof systems. Okay, so here's a little summary of the non-automatability results. And here we have things in between. And here's some other things for which we don't have any non-automatability results. So just a little bit of the historical perspective. So here's a timeline of many of the results regarding automatability. And this is mostly to point out, so the pink ones are positive results, so algorithms. And these are non-automatability results. So there was a lot of work going on from mid-90s to early 2000s. Then there was more or less a gap. And then after Atserias-Müller, there were many follow-up results. So I'll mention a few of these. So some of the early results. So Bus and Ivama have independently showed these results. So Bus showed that determining if a propositional proof system has a proof of size S is NP complete for certain Frege systems. And Ivama showed this for resolution up to some additive polynomial. And then there was a result of, soon after showing that to approximate the length of the shortest proof within a linear factor was hard for several proof systems. Yeah, Tony mentioned this too. And then was the question, well, yeah, what about polynomial? So regarding resolution, this so was shown, yeah, we can't automate in linear time unless P equals NP. Then Alexandrovich and Razborov had, we can't automate in polynomial time unless WP equals FPT. And this actually also applied to tree-like resolution. And they left open the question whether is resolution quasi automatable. Then there was almost simultaneously with Atserias-Müller showing something better than polynomial non-automatability unless ETH is false. And then finally, yeah, Atserias-Müller actually answering the question completely. So this was more or less the story for resolution. And then some of the follow-up results. So there were follow-up results on Alexandrovich Razborov showing the same thing for Nostulitsa polynomial calculus. And then building on Atserias-Müller, there were several. And I think this says something also about how, yeah, this proof was more easily generalizable to other proof systems. So yeah, I'll try to sketch some ideas behind the proof and then also, yeah, mention some related questions. So yeah, one principle that Tony also mentioned is the reflection principle. So the idea is, yeah, I want to encode if a sentence is provable, then it is true. So the unsat version is saying that, well, there is a satisfying assignment to the formula, and there is a refutation of the formula. Okay, so this is a unsat formula. And here I'm saying that there is, so pi is a refutation of f in size S, and n is for the number of variables in it. yeah, there exists f of size n, which has a p refutation pi of size s and has a satisfying assignment alpha. And just the other name for this, in case you've seen, is the refutation principle or refutation of f, but it's the same thing, except I'll fix some f, but this I'll get back to this. And the idea, I guess, what this is capturing is how hard is it to prove lower bounds for a proof system?
Susanna?
Yes.
It's getting late again. But do you want the negation in front of the proof?
Yeah, this is just that there's a proof.
It claims that there exists a proof.
That there exists a proof. Yeah, I guess this is just to say that there is a refutation. That's what I wanted to say.
Yeah, it should have been just reputation.
Yeah, I guess I should have different refutation. That would have made more sense. Yeah.
So L not proof is supposed
That's
to say
supposed to say
is
there
like,
exists a refutation.
I have an encoding pi of a refutation
Yeah.
of f.
Yeah,
Because
I'm
then
sure
it's
I-
unset because you have both a refutation
Yes,
and a satisfying assignment, and
Yes.
that's somehow the field quadratic.
yes, exactly. Yeah. Yeah. Yeah, so I think this question, I think, it really captures this meta complexity question of how hard is it to prove lower bounds for some proof system. So, for example, Lund has this open problem: can AC0 Frege prove super polynomial lower bounds for resolution? And this is still okay. And what Pudlak also showed was that if we take an f which is actually satisfiable and state that there is a refutation of f, which is not true if f is satisfiable, of size s, then there is a polynomial size refutation of this. So this is a false statement saying that a satisfiable formula has a small refutation. So this unsat formula can be refuted in polynomial size. So this is the reflection principle, which is going to be useful for proving non-automatability. So yes,
Whether AC0 Frege has, so then you say like I would plug in a formula which is hard for resolution, and no, one line above.
yes, here.
So I would plug in a CNF formula that actually is hard for resolution, and I give a size budget that is too stingy. And now if AC0 Frege really understood resolution,
Right.
then there would be like a short AC0 Frege refutation of
Yes.
this meta formula, claiming that there is a short resolution.
Exactly. Yes.
Sorry, so what's the weakest proof system that can prove resolution lower bound?
TC0 Frege.
I think there's an old by Pitassi, maybe Coop, the PV, so it's extended Frege. I don't know if it reduces to TC0. Maybe Yano.
I don't know, extended Frege, I don't know about this is zero.
Extended
No?
Frege.
Okay, maybe I'm wrong. It's just from.
But like extended Frege can prove resolution of those?
Yes, extended
Yes,
Frege does
definitely.
prove it. I don't know if this is zero, Frege does.
There is a caveat here that people ignore. It's the measure of the lower bound. It might be possible. It might be that for some lower bound, which is strong, this is hard, but for a slightly lower bound.
Depending on the S. Yeah. Yes. Yes, that's. Okay. So so the overall idea of Seriev Muller. So actually they have this. This is their main theorem, which is the one that implies that. So the idea is that given a formula f, we want to produce another formula in polynomial time, such that if f is satisfiable, A of f has small resolution refutations. And if f is unsatisfiable, A of f requires exponential size resolution refutations. So this is the main theorem that Azarias-Müller needs. And let's just see how that implies the non-automatability. So yes, suppose we have an algorithm that automates resolution in some time. Let's think polynomial for now. So we're proving the first point, polynomial and n. Then we would like to decide whether this formula is sat or non-sat by using this algorithm in polynomial time, let's say. So I can just run my automatability algorithm on this formula here for enough steps so that if it actually outputs a refutation, it means that f must have been sat because there's no small refutation. So that's if f is sat, since I'm running it for enough number of steps, it will output a refutation. And if it does return a refutation, it must mean that f is sat because I did not allow it to run into enough steps so that it could output this large refutation. Okay. So as long as I can construct in polynomial time a formula that has this kind of separation, then I'm done. Then I can prove the non-automatability of resolution. So the idea for proving this, this is a simplified version. Simply choose this formula A of f to be the refutation formula. So the formula saying that f has a small resolution refutation. So the first part I already have from Pudlak, that if f is satisfiable, then this has polynomial size resolution refutation. Yeah, the idea we'll use if f is satisfiable, there is a satisfying assignment, and somehow I can use this to find an invalid step in this purported refutation. Okay, so that's the idea of the upper bound. And then now we need to also prove the lower bound when f is unsat. And here's one way of doing it. Well, there are many encodings for this. One possible encoding will have s times n variables and log n width. Okay, so it will use some kind of pointers for encoding this. But the idea is to show that this requires large width. So to prove a width lower bound. And this can be done by some, if I wrote it here, this, yeah, can be done by some reduction to pigeonhole principle. And then once I have this, I can simply apply the size width relation from Benteson-Victorson and conclude that it must have, it must require some large size. And then I can just choose a parameter s large enough so that this is actually 2 to the n. So the lower bounds would consist of proving a width lower bound, and then we could use Benteson-Victorson. And yeah, and this width lower bound, one way of doing it is by reduction from pigeonhole principle. There's also, this is not how Azarias-Müller, this last step is not how they do it. So they do prove a width, but then they use some kind of lifting to get the lower bound. And this is somewhat of a more robust proof, and it's easier to generalize. So the lifting still preserves the upper bound. And then you can show that you have this, that you can get a lower bound for resolution by this lifting. And then just generalizations of this lifting, you can get lower bounds for the different proof systems. So it's basically, it's the same formula. We just change what kind of lifting we have to use to get the lower bounds. That's the general idea. Yes.
Where we don't have barrier result, it is because we don't have resistance.
Yes. For or because we don't have the width lower bound, the degree lower bound. So for example, for Shirley atoms, we could have a lifting theorem, but we don't know how to prove this the degree lower bound.
Oh,
Yeah. So for that so one way of proving the degree lower bound is via this reduction pigeonhole principle, but this instance of pigeonhole principle is easy for Shirley atoms. So you can't get it through that. So there might be another way of proving the degree lower bound, and then you would get it via lifting.
yes, it's just a short resolution proofs and I don't want
Yes.
large proofs with that proof system.
Yes, yes. So it is some kind of weak automatability. It's not the full weak automatability, but it's an intermediate version. Yeah. Okay. Yeah, so just to say something about weak automatability. So we say a proof system is weak automatable if there is an algorithm that will return some Q refutation, but it's allowed to run in time polynomial on the shortest P refutation. So it can return a refutation in a much stronger proof system and allow to run for more time. And then there are some relations. Some of the things we know about weak automatability. So that canonical pair, NP pair, there is a satisfying assignment that there is a refutation, is polynomial separable if and only if the proof system is weakly automatable. This is what Tony said. If the proof system is strong enough that it can prove its own soundness, then weak automatability is the same thing as having principal interpolation. We also know that resolution is weakly automatable if and only if risk K is weakly automatable, which is if and only if risk K has feasible interpolation. But we don't know whether any of these are true. And then there was also to result that if resolution is weakly automatable, then some parity game can be decided in polynomial time. But it was also shown that this parity game can actually, there's a quasi-polynomial upper bound. So yeah, so this is not such a strong reason to believe that resolution is not weakly automated.
That's two enough. There's two stuff.
Is enough because then you can prove soundness, right? Is that it?
I think so. Yeah.
Is bullet 2 a reason to believe under cryptographic conjectures that proof systems that are strong enough to prove their own soundness are not weakly automatable?
Yes.
Okay.
Yes, that's exactly, yeah. So the non-automatability that we had for stronger proof systems were all non-weakly automatability. Yes.
Yeah, but for example, that piece that is not at all. We don't know how to cryptograph.
Okay, so going back to Gödel, I'd like to point out. So he says that when he's talking about automating, if we could do it in this amount of time, that would mean that the number of steps, as opposed to trial and error, can be reduced from n to log n. Right? So the trial and error would be this. Here n is like exponential in little n, so can be reduced from 2 to the n to some, let's say, poly n. And then later on, he says, well, it would be interesting to know how strongly in general the number of steps in finite combinatorial problems can be reduced with respect to simple exhaustive search. Yeah, so the automatability questions that we've been seeing haven't exactly, they've been addressing this, but we haven't answered how much can we actually reduce. If I want to find a proof of size s, I know I can do it in time 2 to the s. How much better can I do to find this proof? So yeah, can we do any better? And trying to somehow formalize this, I was bold enough to write. Oh yeah, so this is yeah. Is it the case that finding short proofs can require more time than finding long ones? So this is also what Tony said. So I can definitely find a proof in time 2 to the n, but if I want to find one of size 2 to the s, can I do any better than 2 to the s? Yeah. So this was yeah, perhaps too bold, but I wrote this minimum proof size problem, which I tried to make as similar as possible to the MCSP problem. And so here I'm given a parameter s, and I'm given a trivial proof, let's say that the truth table proof of size 2 to the n. And my goal is to output, is there a proof of size s? Can I do this in time poly and s plus 2 to the n? And I think there's nothing known with regards to this. And I don't know if there's any relation to MCSP. So I don't know, maybe something. Yes.
A small question. Can you think of it as you are given the CNN, but it's added to the students?
Sure. Yeah. This is that you don't really have to give a trivial proof. You can just pad it. Yeah. 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 So we don't know how to find the truth, even if I have like time 2 to the middle O of s plus 2 to the n. Yeah. And okay, there are other I think interesting questions I didn't write with regards to automatability, but could be discussed. Like what about if I think of some subclasses of problems? Can I understand automatability there? I think there are many interesting questions that have not been addressed yet.
So if you go back to the MPSP problem.
Yes.
So why s is always smaller than 2 to the n, right? Giving time s plus 2 to the n, you're just saying 2 to the n.
Yes. What I could do is I could give it time quasi-polynomial in s plus poly 2 to the n. I could give even 2 to the little o of s times 2 to the n.
But that's always poly 2 to the n. Or what?
No, I mean if I give depending on what s is, quasi-poly and s could be larger than 2 to the n. So yeah, it's true. Like here it doesn't make sense, but you could think of other functions here that would. Yeah, it's important that the 2 to the n you have the poly, but for the s you could have even like 2 to the little of s, and we still don't know anything.
But do you always want to give 2 to the, you're saying like if I get less than 2 to the n times, the question doesn't make sense. Maybe I'm interested in the full range.
Yeah, so if I do know how to answer this question, right? This is the automatability question. And I'm saying, okay, but what if I give you at least time 2 to the n? So that you can at least output the trivial proof. Now can you output anything close to this small proof? That's the idea.
This is exactly what makes it match the MCSP setup, right? Like you're given the trivial explicit object.
Yeah,
And
yeah,
you're deciding. But actually, I have a question about S. Is it size in number of bits or like number of symbols native to the proof system? Because if you look at like Rahul I talk from yesterday, it's natively like 2 to the S log S to brute force circuits, because you need to write down like where the gates go and the wires, right? Like it's not just the number of symbols. Is there a reason that that's S?
I didn't think too much about it. I guess it would be number of bits if you want to actually do it into the S.
I think if you think about a correct proof system, then you would just look over the inputs to the function, right? So it should be the number of bits.
What about the non-deterministic answer? The non-deterministic version of this, shouldn't it be if it's analog of MCSP? What about asking if you have a short proof of a minimal proof? The minimal proof size is this.
A proof that the minimal is something.
Yeah.
So this is the algorithmic version, and you're at the deterministic version. You're also in the non-deterministic version.
Makes sense.
I think it makes sense. Yeah. Yeah. So think about it.
Yeah, I was just gonna ask, is there anything are there any non-trivial algorithms for, right, to do better than 2 to the S?
Not that I know of, and not even for tree-like resolution.
You can't
So
even play.
if I want a proof of size S, I don't know how to do it in 10 less than 60 S even for tree-like resolution. So, yeah, this is the last slide. So just some open problems. So some obvious open problems is to show that it's NP hard to automate these proof systems, which are proof systems for which we know how to prove lower bounds. And as we saw, part of showing this NP hardness required proving some lower bound. So maybe it's possible to show NP hardness for these proof systems. Also, here we don't know of any automating algorithm. Can we show it or show that it's not possible? The same holds for cutting planes. We don't know any automating algorithm. Can we show that there is or that it's not possible? Same for ResK. And then there's some questions still here about coefficients in order to actually automate this in time n to the d. So just understanding coefficients better there. Then there are also like other tree-like proof systems, like tree-like cutting planes. It could be easier to automate, or maybe not, or maybe we can show NP hardness of automating tree-like cutting planes. We don't know. And the reason is that the upper bounds actually require this DAG-like structure, the upper bound that Atzerias-Müller has. So yeah, that's why also here we can only show ETH hardness. Then yes, of course, understanding better weak automatability in resolution. That's it. Thanks.
More questions for Susanna?
Just to understand the gap between this ResK and this reslog, what's the statement for ResK? Is it like 2 to the n to the minus k, or?
Yeah, I think I wrote it. Let me just go back a bit. The 15 here. Yes. So you have yeah, you lose this factor k. So in k, you can get it a little bit more than constant, but that's not too much.
Maybe it's good to point out that like for reslog, we don't have any lower bounds or any function. Or it's like all the ResK lower bound techniques break down by reslog.
Right, it's like this.
Compressing down to
Yeah, this weak switching limit doesn't work.
Okay.
Hi, Susanna. So I'm just curious, when you mentioned the hardness of automating tree-like resolutions, you had also a result on the randomized ETH,
Right.
which was a little bit stronger.
Yes.
So is there any intuition you can give to us why it changed?
Oh, yeah, this is because of expanders. So we need some bounded degree expander from n to n squared, and we only know how to do this randomized. So if you can have a better construction of unbalanced expanders, then you would get a better result.
Any questions? So then we should thank Susanna again. I guess we should also thank Rahul, Rafael, Tony, Valentin, organizers of the bootcamp.